Hello everybody and welcome to my presentation for the 9th International Conference on Renewable Power Generation. My name is Ahmad Hosseini, a PhD student at the University of Mons, and in this video I will be presenting the impact of fast wind fluctuations on the profit of a wind power producer jointly trading in the energy and reserve market, which is in collaboration with Power System Market Research Group of Mons University and University of Ghent. Nowadays, wind power producers are equipped with advanced control technologies for controlling the wind turbine's output power. At the same time, market policies are evolved such that wind power producers are incentivized to participate in the joint day-ahead energy and reserve market. Therefore, wind power producers are seeking to allocate the optimal share of their output power in the energy and reserve market floor to obtain a higher profit. However, their expected profit is affected by some sources of uncertainties, such as wind speed, system frequency, and etc. In that regard, deviations from the scheduled bids at each market floor are financially compensated in real time. Deviations from the day-ahead energy bids concerning the energy market is settled every 15 minutes through imbalance settlement. On the other hand, deviations of the day-ahead reserve bids regarding the reserve market are settled at the balancing stage at a much shorter time interval, namely 10 seconds. As you can see, the stochastic behavior of the wind speed appears in two different time resolutions: quarter-hour wind speed uncertainty and 10-second wind speed uncertainty. In the literature, several studies are conducted to consider the potential partaking of wind power producer in the reserve market as well as the energy market. The actual wind capacity available in real time, accounting for inherent fast wind speed fluctuation, is not considered in these studies. In other words, these studies used 1 hour mean wind speed uncertainty to represent the stochastic behavior of the wind speed at both 10-second and 15 minutes time resolution. Therefore, the goal of this study is to evaluate the impact of fast fluctuations of wind speed on various revenue streams of wind power producer participating in a joint day-ahead energy and reserve market. As for the methodology, first we develop a stochastic bidding framework in which wind power producers submit a conservative reserve bid to the market to ensure that it is able to fulfill such a power capacity in real time. Then, we apply an extensive ex-post analysis on the outcomes of the stochastic bidding model. The two-stage stochastic bidding model is as follows. The objective is to maximize the profit of the wind power producer in the market. This term is the contribution of wind power producer in the day-ahead energy and reserve market. The remuneration regarding the deviation of the energy bids is represented by this term. The revenue associated with the real-time activation of the reserve is yielded by this term. Here is the weighted sum over all scenarios. The constraints of the bidding model are shown here. Then we apply the ex-post analysis. First, let's look at the imbalance settlement. In here, pi plus and pi minus obtains the penalty or payment for the deficit or surplus of generation in real time. By adding the contribution of the day-ahead energy bid to the pi plus or minus, we obtain the actual profit of the wind power producer in the energy market. Similarly, at the balancing stage, the actual revenue of the wind power producer regarding reserve procurement is obtained by subtracting the contribution regarding the day-ahead reserve bid from its associated real-time penalty. Also, penalty for failing to activate the called reserve in real time is obtained as shown here. Now is the turn for numerical results. We apply our method on a 5 megawatt wind turbine model, and we consider two cases. In case 1, we assume that we have perfect information of mean wind power for the next hour through an idle forecaster. In case 2, we take a set of scenarios to represent the mean wind speed uncertainty. Then we apply the outsample analysis. We take 10,000 samples of wind and system frequency signals with 10-second resolution. In case 1, where we have the perfect information of the wind power producer through the stochastic model decides to allocate all the power in the reserve market, and that is since prices are more beneficial than in the energy market. As you can see in this plot, the average normalized net reserve activation revenue, which is shown by plain black curve, is below zero, and it means that the wind power producer is not able to meet the required reserve activation. As you can see in this table, wind power producer obtains only 39.60% of its expected in-sample revenue regarding procurement and activation of reserve in real time. Here are the results for case 2, where we are taking a set of scenarios representing the hourly mean wind speed uncertainty. In this plot, you can see the in-sample results, which are obtained by the stochastic bidding model. In this case, wind power producer decides to participate in both energy and reserve market. The plain black curve shows the bids for the energy market for a range of spot market prices, and the dashed line shows the reserve bid. The blue dotted line shows the total in-sample profit of the wind power producer. Now let's look at the out-of-sample results. The black solid line here shows the normalized actual revenue of the wind power producer resulting from the day-ahead energy market and imbalance settlement. As you can see, on average, wind power producer loses between 2 to 19% of its expected revenue regarding energy market and imbalance settlement. And it is because we are approximating the 15-minute wind speed uncertainty by a 1-hour window. As for the reserve, you can see the solid black curve, which shows the average normalized net reserve activation. The blue lines shows the normalized standard deviation. It is seen that wind power producer faces many periods during which is unable to procure or activate the required reserve. In this table, you can see that wind power producer obtains about 85% of its in-sample expected revenue for reserve bid, which means a 15% loss, and it is since we approximate the 10-second wind speed uncertainty by 1-hour window. In conclusion, the impact of intra-period wind speed fluctuations on the profit of a wind power producer participating in the joint energy and reserve market is assessed in this study. Despite using a conservative model in dealing with the reserve power violation, the numerical outcomes for both cases confirm that the revenue considerably deviates from its expected value. Therefore, decision makers should devise new bidding models to better reflect the intra-period wind speed fluctuations in their stochastic optimization framework. Also, day-ahead probabilistic forecast tools regarding short-term uncertainty should be developed to capture wind speed variability in higher resolution. Thank you for your time.